started on the talks that's coming right now. So our very first speaker is Professor ZhuHan from University of Houston. So Professor Han, he received the Bachelor of Science degree in Electronic Engineering from Tsinghua University in 1997, and the Master and PhD degree in Electrical and Computer Engineering from the University of Maryland, College Park in 1999 and 2003, respectively. Currently, he is a John and Rebecca Morris Professor in the ECE as well as CS department at the University of Houston, Texas. So Dr. Han is a IEEE Fellow since 2014 and a AAAS Fellow since 2019. Dr. Han is a 1% highly cited researcher since 2017, according to Web of Science. The Dr. Han is also the winner of the 2021 IEEE Kiyo Tomiyasu Award for outstanding early to mid-career contributions to technology holding the promise of innovative applications. So without further ado, let's welcome Dr. Han to give us a speech.
Thank you very much for the invitation. Okay, please allow me to share the screen.
Yeah, just go ahead. You can go ahead and share your screen.
Okay, sure. Can you see my screen?
Yeah, I can see it.
Yeah. Oh, thank you very much for invitation. And I have to admit that, okay, I only do this kind of chip design in my early career. So I'm not a chip design person. However, we in our group, we recently indeed working on the machine learning and also this kind of for this kind of automobile industry like the Toyota. And here we want to share our recent study and hope that okay, this give a kind of potential kind of interest and potential directions to the Silicon Valley friends. Okay. And also, this is a collaborative with many of my kind of former students as well as this kind of collaborators, and also supported by National Science Foundation, Toyota, and Amazon. Okay, so here we talk about some background about what is feather learning, and then okay, we talk from this optimization, machine learning, and optimization point of view. Then specifically, we concentrate on this vehicular network, and we talk about some our project with Amazon, augmented reality kind of example, and then also we do this MEC multi-access edge computing kind of example by using the machine learning. And then next, okay, we try to upgrade from the feather learning to feather analysis, and then we talk about one example and for this kind of data skewness. And finally, we have this conclusion. So here, why we need kind of, why the data live in the edge? Because we have billions of phone and IoT. And if we take all the data to this kind of cloud, to the cloud center, the communication burden is too high. And also, okay, in some applications, especially real-time applications, the round trip delays cannot acceptable. For example, most of our kind of data center is in Montana, mine in Montana, because the cool weather and also the power there is cheaper due to the hydrogen. So in this case, okay, this latency cannot be acceptable. So we have to compute over this edge or even at the devices. And also, okay, because the communication typically, okay, especially for wireless communication, this can cost a lot of energy, maybe 10 times more than this computation time. And so this can also save the battery life. And moreover, this is a privacy issue because I really don't want to, take my iPhone, okay, upload my photos to the server to do the machine learning, because this can be a kind of privacy issues. So, okay, now the next question is that, okay, if we keep on this data into the edge, or to the user. So what we want to learn and what we want to analysis. So maybe 5-6 years ago, okay, Google proposed this feather learning kind of a framework. So what is a feather learning? So instead of taking the data back to all this to the server at the beginning will have this kind of initial machine learning parameter, and for example, like this one, and it will propagate to all the users. And this is a broadcast to all the users. So this is very simple because you only broadcast the parameters. And then all the data begin to collect the data, all this white circle is data. And after that, they will not transmit the data back to the server due to the privacy issue and the communication issue. Instead, they try to learn by themselves, okay, try to upgrade the data. And after upgrade data, they will only report the changes or the new weighted vector back to the server. And then the server will try to aggregate them and without knowing the client's data. And then after that, the new data, the new kind of machine learning is parameter is updated. And then the next round is broadcast to the out client again. So for any client in the next round, it will get the data, we will get this machine learning model trained not only by its own data, but also by the others' data, while the privacy and communication can be kind of improved. So this is the basic kind of federal learning, and it was one of the biggest kind of machine learning kind of story during the last 4 or 5 years. And so this is repeated until the convergence. Moreover, you have other advantage. So we all know this story. We have 5 different people try to see this blind, 5 different blind people try to see the elephant. And then because they only observe the local data, so they can only see part of the information. But by aggregating them together, okay, they can have the whole picture. So basically, this is a kind of another advantage of the federal learning. So this advantage is at least here, the first one, they can handle the non-IID data. There's 5 different blind people touch the different place. The communication cost, you only need to communicate this kind of the machine learning parameters instead of this raw data. And then user privacy obviously can be saved. And from the optimization point of view, okay, typically they're using the Bible algorithm called feather averaging. So basically, okay, at first the model try to select the random initialization, and after that, okay, they randomly select a set of clients and then try to sample them. And after that, okay, they try to perform this kind of a local gradient descendant method to improve their performance. And then after that, okay, they aggregate the information and then to go to the next time round. So this is basically, okay, from optimization point of view, okay, how the federal learning is doing. It somewhat look like my research group. Okay, I have my limitation, okay, I don't have that bandwidth to cope all my 15 PhD students. And so what I will do is that, okay, at each day, okay, I go to the lab and randomly select the few students that I happen to talk for a period of time. And then I got an update. So this is just a kind of small set. And based on this update, I try to change the gradient, give them the guidance. So in the next few days, if they don't meet me, okay, they will continue to this gradient until the next sampling point. So this is exactly what this kind of federal learning algorithm is doing. And okay, so I give some kind of background about the federal learning. And then the next one I want to cover is how could this one use in the vehicular network. And then, okay, we have this kind of, we have 6 years of collaboration with Toyota already. And here is some of the results we show. And most of them is about the computation and machine learning and edge computing. I don't know how much this one will related to the chip, okay, but I hope that, okay, maybe the expert here, okay, can provide more kind of insight for that. So here, okay, basically, we want to the Toyota to provide the virtual object to this kind of, I mean, to the real world context. For example, nowadays, okay, if you go to buy a Mercedes-Benz S, okay, instead of they will have the head-up display, so they put the map and also some important information projected in front of the in front screen. So in this case, okay, the driver can see the information more immediately. So the challenge is that, okay, we need to have the real-time interaction, and we know to know exactly the location and also prevent the delays and also the accuracy. So for example, okay, when you drive on this kind of highway, okay, the machine learning will recognize for the different kind of place, and then okay, they can maybe give some advertisement, or maybe okay for some kind of pedestrian or some kind of dangerous, they can give certain warning for this on the front screen. And this is a example for AR, but it's on your phone. Okay, later we will show you on this kind of vehicle case. So here on the bottom, okay, you have the different user, and they may have the different kind of requirement for the augmented reality. For example, lane and passing or some kind of other activity. And then okay, we have the this edge server. Okay, edge server at the beginning they may have this randomly select some devices and download the naive model, and then on the they have the local update, and every time okay the driver do something, it is just an update for the machine learning. Okay, because machine learning predicts something, and if the driver try to do the other things, probably something wrong. Okay, so basically they can have some kind of local update for the machine learning. And then after that, this weight is sent it back to the server, and the server try to do the average according to certain weight, okay? And then finally, this kind of new model is sending back to the devices. Okay, so by doing this one, you can see that, okay, all this kind of data will keep locally, and the communication between is just a kind of weight. And this is kind of real-time update. They try to update for the high definition map. The so-called high definition map is that, okay, this Google, they have a different layer, okay? Maybe the road map, the street map is the lowest, is a fixed one. And then Google map maybe give you some kind of traffic information, but the high definition map, okay, all those cars around the traffic light, maybe we'll talk with the edge computing to give a kind of real-time description about the car location and the pedestrian location. So by doing this one, okay, they can kind of improve this traffic and also reduce the accident probability. So here I show a video online. This is by Huawei. Okay, I can also show this kind of Toyota one, and so you can see this is a head-up display in the front screen. And for example, this a pedestrian walking from the right to the left, and I can see it, but the car on my left cannot see it. And then okay, even with a Tesla self-driving, I don't think it can see it, because the Tesla only work for the Tesla kind of unmanned driving only the local machine. They are not communicating with each other. However, from the Toyota perspective, okay, if we have the edge computing around this kind of corner, and then the nearby car can form the high definition map, then my car see this pedestrian walking from right to the left, can warning the other kind of driving car nearby. So by doing this one, okay, we can prevent this the accident from happening. So basically, this is the story that we are trying to talk. And then, okay, so in this case, we have this kind of conventional edge computing for the internet, this kind of edge, and then they can have this kind of they can have either this 4G, 5G, or Wi-Fi related. They have the limited storage, computing, and the battery. And then, okay, we design the system architecture, which is specifically for vehicular scenario. Because of the vehicular scenario, the car moving is predictable, and also okay, and also for this the constraint and the requirement is also different. So basically, okay, we designed this one for this augmented reality on the board, and also the roadside unit, where we locate the roadside unit, and also the edge. All these things will be make the difference. Okay, so we want this kind of, it's not wearing the AR, when you're driving, you don't need to wear the glass, okay. So basically, okay, we will find the nearby surroundings, and then, okay, we have the real-time object detection to see, okay, maybe there's a kind of a different store around. And then we try to perform the eye tracking, And so basically telling you, okay, where you are focusing. And I think yesterday, right? Yesterday, this TikTok CEO tried to report for the Congress, and the Congress asked the question, why you do the eye tracking? I think most of this social media do the eye tracking, basically telling you, okay, where your interest is. And then after that, okay, they fetch the data for area of interest. For example, when I'm driving and suddenly I saw a Starbucks nearby, and I mean, from the eye tracking, it looks like I'm looking at it, focusing. Then in this case, okay, we will get this kind of downloaded information. Maybe okay, immediately okay, the car understand me that I want to have a coffee and then send me some coupon. Okay, this is a story, and here is an example. This is a kind of our simulation, and we show that when we driving, and then okay, maybe we have Rao Mian King. Okay, in this case, and the next one is trying to see the stop sign, and then also the other vehicle. So basically, okay, by looking at a different location, the system can provide this kind of different information, either the different information, and then okay, especially this restaurant example. So basically, okay, the Toyota want to have this instead of want to be the self-driving company or this and because in the future, okay, the autonomous car, okay, when the autonomous car becomes reality, I think the number of cars needed will be significantly reduced. Because in the future, if everything autonomous car, we probably will download some kind of app, and then okay, like Uber app, and then we call for the unmanned driving. So this will significantly reduce this number of car needed. So the Toyota want to look ahead. For self-driving, it's hardly to compete with Tesla, right? So they want to be this kind of service provider, edge provider for this kind of future unmanned driving. Okay, so this is a basic thing, and I think I need to speed up a little bit. And then we have this kind of another case. So typically for the federal learning, you have one task and multiple devices, and those devices have to finish the task unconditionally. However, okay, it might not be the case because my phone doesn't make sense to make a kind of task in Bay Area, right? So basically, they have this kind of selection. So, and also it cannot handle this kind of, large problem. If we select the task with devices and select the devices for the task, this is a kind of the complexity for find the optimal solution is n to the power 2. So in this case, even power 4. So this one we introduce this marriage. So basically a matching game. So basically we have the agent, a size of man, a size of woman, with a size of edge node and size of this a task and size of devices. And then we have the preference list. Okay, I prefer this one to that one. Okay, and after that, okay, we want to generate something that don't have the blocking pair. So what is the blocking pair? The blocking pair is a married man prefer a married woman, and this married woman also prefer this married man. So in this case, okay, these two couples get divorced, and these two, this male and female get married. So we want the matching, which is not to this kind of, no blocking pair. So in this case, our goal is not social optimal, but stable matching. However, because everybody wants the one on the top of the list, so it must be near optimal. And also the Gale-Shapley algorithm, which Shapley won a Nobel Prize 8 years ago, and basically can reduce the complexity from n to the power 4 to n to the power n. And here is an example. We have this this kind of preference list for man. Adam likes the guitar most, so he did guitar, and Bob like Irina, and the cars also like guitar, and guitar think Adam is tall, handsome, and rich, and then Adam have to find the second preference list, and David also PK Bob, and then yeah. Anyway, so it's reached stable marriage very quick. How quick it is? My PhD student converts in 1 semester. Yeah, but the problem is that, okay, you don't need to have, this algorithm needs the preference list for all the devices and all the tasks. which is impractical, or impractical, not possible. So my student are trying to have the incomplete list and show that, okay, it's close to the optimal. So how many minutes I have? I don't, hello?
You still have 5 minutes.
Okay, sure. Okay, in this case, let me go quickly to the further analysis. So compare with this HAN analysis proposed 2 years ago, 3 years ago by this Google again. So basically upgrade the further learning to the to data science. So basically, okay, in addition to this, instead of updating the machine learning parameter only, and or try to do the simple average, they introduce the data science into the picture. So basically, okay, if you want the devices instead of providing you a kind of a machine learning model, they provide you a data science insight. For example, my first PhD student, okay, when he tried to find a job, and my friend tried to call me, okay, is he good? And I just reply, okay, if I reply, his GPA is something, how many papers he published, this is a further learning. However, I reply this kind of things like, okay, he can finish the deadline. This is my insight to him. And immediately the aggregator, the employee, try to average the information and then can get this idea. And also this, so basically introducing this kind of data analysis into this picture. And so basically this is the case. And compare with this further learning, we have this kind of data science, not only from this kind of server point, from the user point of view, but also from the third aggregator. Aggregator will do this kind of Bayesian tree, all the different algorithms together, and also compare with the data mining. Okay, we are also different in the sense that, okay, the data is a state as the original, and also we care about the data heterogeneous more. Okay, and here we try to use further analysis for this kind of, data skewness. So nowadays, when we read this kind of social media, they have a lot of things, all the spectrum. Okay, they have extremely left, extremely right. So how could we get the data? So basically, we have two steps. The first step, we try to use Hafting inequality to quantify this. On the left figure, okay, we have the left median or right median, but I can average a median kind of in the middle. So by Hafting inequality, we try to quantify this kind of left and right by a certain value. And then by using this value, we use a multi-arm bandit problem, which is a type of machine learning to do the exploration and exploration. For the median in the middle, okay, we will converge, we will kind of read more. For the median extreme left or extreme right, we will have in this case, this skewness number is large, then the probability to sample it will be low. So in this case, we can significantly speed up the further learning, and by 66% and 4 times. So this is a basic story. And finally, we have the conclusion. So further learning is a major kind of part of the machine learning paradigm. And the good thing is that, okay, it's a distributed client. There's no also address the communication bottleneck and the privacy concern. And then we try to explore this kind of integration of the further learning into the different network, especially for the vehicular network. And then hope this give you a kind of taste about the machine learning and the vehicular network. And finally, okay, this is our lab. For all the other information related, you can go to our website. Okay, thank you very much.
Thank you very much, Professor Ham. I think that was an amazing talk. I think even in that 25 minutes, I learned a lot. So every time when I, heard a talk from the professors, it's always, a lot of things, and always a lot of things, fruitful thoughts. So I really enjoyed that. I'm pretty sure, all the audience here also enjoyed that. So so now here I see there's a question on the chat room. And by the way, everyone, please free to submit your question in the chat room, and then I can pick it up and ask Professor Ham. So the very first question is, you mentioned about for the car, by doing this federated learning rate, you kind of reduce the communication cost. You don't need to send that much data, right? So the audience is interested about, can you estimate the required mobile bandwidth, say per mile of road, to make this technology meaningful?
Yeah, I think, I mean, currently, okay, for this kind of 4G, 5G, okay, I will say that for video transmission, so suppose you take all the video back and then do the machine learning at the edge computing, that is not acceptable because, you know, for this video, especially high definition video, the bandwidth is, I mean, this kind of transmission, the bit per second is too high. However, here we don't report this kind of, I mean, we don't report the data back, right? We only report some kind of machine learning parameter. And even more, okay, sometimes we use a fuzzy logic. For example, that I showed the video, the pedestrian walking from the left to the right. So instead of sending all this kind of a detailed description, we can just sending a warning. I mean, maybe, okay, pay attention, or this kind of just yelling, okay, then everybody just panic, okay, nearby car, then try to prevent this hitting this guy. So in this case, the communication is very small. Yeah, we have already, we indeed consider this communication, and I think it's acceptable. Yeah.
Okay, thanks a lot for the answer. And before we move on, by the way, I just really want to show you that, you know, the analogy that you made just now about when you go to the lab, you just randomly pick a few students to talk to. That was really interesting. And again, thanks a lot for, you know, giving us this speech. So now let's